Before I hand over to Vibora, I'd like to welcome you to the DANUBIUS modeling node webinar. And here in the studio at Deltaris, we have myself, Björn Backerberg, and Joost Ike, supporting Vibora, Georg, and Francesca in delivering this webinar. And I hand over to Vibora to give us an introduction and a code of conduct. And I will be managing the slides from the studio here. So just say next slide if you want me to move forward. Thank you, Vibora.
So thank you, Björn, and thanks to all the participants to join this, I hope, really fruitful 2 hours webinar. So thanks to you from the organizing group, and Björn, are you?
Yeah, I'm controlling.
Can you go to this? So go to the second slide, please. Quickly, the code of conduct. Please mute your microphone when listening, and for the speakers, when talking, unmute the microphone and show yourself with the webcam. For all the participants, you will see there is a box where you can write question during the presentation. We will have the second hour to discuss, so just right there, and eventually to what speaker you are referring. The webinar will be recorded, and here you can find the link, and more or less that's all. Second slide. So why we are here, just a small introduction on what DANUBIUS RI is. DANUBIUS RI, the International Center for Advanced Studies on River Delta System, is a pan-European distributed S3 research infrastructure based on and interested in supporting interdisciplinary studies on river sea system. River sea systems are really complex systems, and we consider them as a continuum, and many challenges are connected with the river sea system from a scientific as well as from a societal and environmental point of view. Just to mention some, and these are the results of the discussion of the last year of the DANUBIUS community that led to a scientific science and innovation agenda that you can find in the website. River sea systems are facing problems and need to ensure sufficient flows on water and sediment, maintaining structural integrity and continuity, preserve biodiversity, and try to facilitate the natural processes there. But river sea systems are as well hotspots for climate change and are exposed to extreme events. And the vision of the research infrastructure in supporting the activity of the research community is to try to reach and achieve a healthy river sea system and to advance the sustainable use of the resources present in this system. Click, please. The research infrastructure is providing state-of-the-art facilities, expert support, and are trying to support the work of researchers in providing excellent interdisciplinary science. We are trying to cross the borders of disciplines and trying to fill the gaps and overcome the current fragmentation in science, eventually, and trying to answer the questions and the requests from society. We identified 4 research areas that are global change and megatrends: water and sediment, biodiversity and ecosystem, and multiple impacts on river sea system. And this is the science and innovation agenda that now is present. But we are asking you, the community that are working on river sea system, to help us, because DANUBIUS as a research infrastructure and the studies on river sea system are a living body and are living processes, so they will be updated based also on the needs of the community. Slide. The research infrastructure is divided in components, has 4 thematic nodes. the observation, the analysis, the modeling, here we are, and the impact node, and 12 super sites, so 12 river sea system in Europe that are our first living labs to test this interdisciplinary research. DANUBIUS has the goal not to stick at the European level, but to try to develop interdisciplinary research to spread and to share worldwide with the other systems and other research communities. The infrastructure is led by Romania, and there is a data center and a hub in Romania, as well as a technology transfer office and an e-learning office. Slide, please. The modeling node is addressing two different aspects. One requested by you, the modelers, that is a need of complexity to increase the potentiality of the tools that we are using, to share knowledge, to try to add possible technical and scientific development to go deeper in the modeling investigation. But as well, we are answering the request of the stakeholders and the end user, those that use our results or use our tool in simplified ways. And this requires an effort also in trying to simplify. In the last years, we identified 4 working groups and around main teams that perhaps now need to be updated and filled with the knowledge and also your contribution. They are listed here. So special integrated models in river delta sea system, interchange format standardization and input output, post-processing, and water quality and pollution model. Slide, please. We will have a really short but effective overview on what we all are doing in the different systems we are studying, what challenges and what bottlenecks. And we will try then to develop a discussion around these, trying to share our experience and trying to overcome some of the gaps that we found. Slide. Hopefully, we will have a major involvement also of those of you that did not hear about DANUBIUS before today. They are all welcome to join the discussion in the community. And perhaps we will be able to refine the list of priorities, identify new topics, and eventually also try to do some problem solving, sharing our experience. For now, it's all. I leave the floor to the colleagues and all the other speakers.
Thank you, Vibora. So we're now moving into a session of lightning talks. So I will manage the slide deck from this end. So as Vibora did, please just say next slide or something of that sort. I'd like to introduce our next speaker. His name is Thomas Berudi from the Federal Waterways Engineering and Research Institute in Germany, I believe.
Yeah, good morning, everybody. You can hear me?
Yes, perfectly fine, Thomas.
Okay, thank you. Thank you, Björn. I'm like to introduce me a little bit. I'm head of the section Numerical Methods in Hydraulic Engineering, as you said, in the BAW. And I will speak about the coupling of numerical models of 2 supersites, the supersite Middle Rhine and the supersite Rhine-Meuse Delta. The next slide, please. Yes, I will start with some facts about the supersites. The supersite Middle Rhine, which is hosted by the BAW, covers the free-flowing stretch of the River Rhine from Iffelsheim. This is the last barrage of the Upper Rhine to the German-Dutch border. The stretch, which is marked on the right figure, black, is about 500 kilometers long. The supersite Rhine-Meuse Delta, which is directly connected to the supersite Middle Rhine, it's directly downstream. This covers the delta region of the Rhine, as well as the medium-sized river Meuse and the part of the North Sea. Both supersites have common challenges, common issues like sediment budget, sustainable navigation, the climate change, and so on. But only together, these super sites form a complete river sea system. Next slide, please. Yes, consequently, the coupling of the numerical models of these both super sites is a very clear way or an obligatory way to match the objectives of DANUBIUS. These objectives are the understanding, the integrated understanding of the functioning of the river sea systems, as well as the transboundary research on the river sea continuum. To reach this vision, we are planning an external coupling of the existing hydrodynamic models. And for long term, we are planning continuous transboundary models as hydrodynamic models as well as morphodynamic models. The next slide. What is our actual progress? It already exists a Dutch-German working group which has been established by the shipping authorities, the German and the Dutch. This working group focuses on numerical models concerning the sediment management and the navigation only. At the moment, this on the one hand, on the other hand, at the moment we are completing at the BAW the chain of our hydrodynamic 2D models. These models are based on the finite element code Telemark. As you can see on the figure on the right side, only a small gap at the middle line remains actually. Furthermore, we already developed a new high performance code for shallow water flow at the BAW. This code is based on Dumux. It's a modern programming environment which offers a very massive parallelization. Next, please. Yeah, what are the bottlenecks and the challenges? The most important are the huge modeling areas, which require high performance computing, especially if we choose the continuous models for both super sites. Further challenges are the interfaces between the different model types if we choose an external coupling of models. And also we have to harmonize the modeling data, for example, the different coordinate or height reference systems. Next, please. Yeah, what are our future work in the framework of this Dutch-German working group, which I mentioned? Morphodynamic 1D model of the Waal in the Netherlands will be extended to a part of the Lower Rhine in Germany. This means extended upstream already now. Also, an extension of our existing 2D models at the BAW to the Netherlands is proposed for the next future. Concerning the code development, we are still working on the performance. We are working on a fully implicit code to have very high performance, and at the moment we are implementing the morphodynamic model. Yes, and last but not least, for all these topics, for these challenges, a close collaboration between the German and the Dutch authorities, as well as the super site coordinators, is essential to succeed. Yeah, thank you. I hope I will be in time, and we'll have the questions after.
Thank you, Thomas. Much appreciated. Thank you very much. Just to remind the audience that if you do have questions, please use the questions functionality in the GoToWebinar, and we will address them in the open panel discussion afterwards. I'd like to introduce our next speaker, Joanna Staneva. The floor is over to you.
Hi, good morning. Can you hear me now?
Yes, perfectly fine.
Okay, so just to introduce myself briefly, I'm Joanna Staneva, coming from Helmholtz Zentrum Geishach in Germany, and I lead the Department of Hydrodynamics and Data Assimilation. And we are working together with several other colleagues, which I want to acknowledge, on the Elbe estuary, but also on the 3 estuaries of the German Bight. Next slide, please. So what are the background of our activity? Still, it is for the common community, a common question. Is coastal ocean modeling nowadays mature enough to address the different practical issues from the different scales, for example, coastal engineering, but also search and rescue, including water quality, green energy in connection with offshore wind energy, but also to provide reliable services for coastal management response to climate change. And to answer these questions, we are still developing and implementing novel approaches, which include the German Bight and downscaling to the 3 estuaries, namely the Elbe, Weser, and Ems estuaries. And these novel approaches are currently needed in order to understand the general context of both the climate change, but also the coastal hazards. But they are also triggered by the increased interest in reducing the prediction errors at the coastal scales, because it is very important that we increase the operationality of our system, which is also relevant to predicting better the extreme weather events in the marine realm. What is also challenging nowadays is the bridging the novel Earth observation data, for example, the satellite information, which is nowadays with a high resolution, together with the high resolution coastal models. And we want to study the impact on climate change and also to do coastal prediction. And all this has a wider social impact. Next slide, please. And in order to do that, as I mentioned, we develop a coupled system for the 3 estuaries using a structure grid model schism, which is a 3-dimensional hydrodynamical model. And this model also is coupled with biogeochemical model, a COSMO, with sediment model, with a wave model. And we are now also working towards coupling it with atmosphere model. But coastal and estuaries model, especially if we want to increase the operationality of our system, are nothing if they are not connected from one side with the regional model and from another side with hydrology. And recently, we also use the HD model information and performed the hydrology experiments in order also to study the response of the estuary system, for example, for the different flooding events. And we also develop and prepared a different set of criteria in which we want to extend the existing operational products, for example, the Siemens product, towards an active coastal fringe, in which we also address the requirement of the different boundary conditions, also in terms of the driving term and the derived field. And all this is in order to improve the presentation of our coastal model predictions, which is also required by many stakeholders. Next slide, please. And just very briefly about the recent progress, because I know we were present also in the previous DANUBIUS meeting. As I mentioned already, the 3-dimensional hydrodynamics models are coupled with also 3-dimensional ecosystem model, which is a COSMO model. And we use this coupled model in order to deliver a realistic picture of the dominant estuaries, for example, eutrophication. And you can see here the dissolved oxygen along the Elbe estuary, and it nicely simulates the oxygen minimum along the Elbe estuary, as well as the well-mixed estuary oxygen and a stratified situation near the estuary. But we used also this model and different model state variables in order to derive downstream products, for example, risk maps for water quality parameters like oxygen concentration And the patterns below show the organic sediment and also the near bottom dissolved oxygen in the Hamburg harbor. So you can see here, this is a very high resolution model near the harbor. Next slide, please. And what are the challenges? As I already mentioned, and this is an issue for all from river, estuary, and coastal problem, is that we are dealing with the diversity of model components, which is also required, and this is demand of the end users. It is not nowadays only a simple hydrodynamical model, but it also includes biogeochemical models and waste model. But all these models, they are not if they are not connected with a larger scale model, because all our estuaries model are too much dependent on the situation of the larger scale model from one side, and from the another with the atmosphere wave interaction processes. And as I mentioned already, another challenge is finding out a clever way of connecting the coastal and estuary models with hydrology model, and we are still working on that direction. In addition to that, it is important not only on the global and regional scale, but also on river and estuary scale of increasing the synergy between the newly available data and the coastal model. And this issue will become more and more challenging with availability in the near future of the very high resolution satellite data like SWOT, which provides a nice information not only for the coast and estuaries, but also along the rivers. And it is also a relevant issue to increase the operationality, but then also a smart operational design is needed for that, taking into account the end users and society demands. Next slide, please. And these are the proposed future work in that direction. We will continue working on the water quality. We will focus first on the Elbe estuary, but further we will upscale from Elbe estuary to the coast, also including the other two estuaries. This will be further integrated with the sediment dynamics and morphodynamics, which is also very relevant, especially the response on the deepening along the Elbe estuary. Another important issue is to increase the predictability and doing also the pollution modeling, which will nicely connect the land-ocean continuum and also studying of the fate of the pollution from the land source to the ocean. And as I already mentioned, increase of synergy of available observations and unstructured grid model, which as a beginning can include the ocean observing experiment, which to all my knowledge are not yet available at the river and estuary scales. And as a last challenge is to produce the climate scenarios in order to study the natural variability and human-induced changes. Thank you. Do you have any questions now, or we will discuss it later?
Thanks, Joanna. No, we will discuss questions later if they are raised.
Okay.
Thank you for the presentation. That was really great. Next, I'd like to welcome back Vibora.
Yes, here I am. Hi again to all. In these 5 minutes, I will try to sum up really shortly what is our experience at the CNR on modeling the North Adriatic, the supersite Po Delta North Adriatic Lagoon. Please, next slide. The work at the CNR based on the well-established model that was created at ISMAR and is called the SHIFM, is a 3D finite element unstructured grid model. it was created there, but developed in a community. So we will see also later the contribution and the implementation done by other institutions, like, for example, OGS. The model was born addressing a transitional environment, hydrodynamic reproduction, and in these decades developed studies on storm surge modeling, sediment transport modeling, Lagrangian modeling in 2D and 3D for ecological studies, as well for practical activity like search and rescue, or recently also marine litter. Next slide. We applied the model in the lagoons, in the delta, trying to connect the Po Delta with the coastal areas. And we don't mention all the application, but just the fact that some last studies done in the Po Delta that were addressing process studies connected with coastal mixing and salt intrusion in the climate change perspective allowed us to push the model and to try to do some development connected with the model. So let's say we start from the scientific question, and then we try to adapt the tool, adding the requested algorithms. In the recent years, we also tried to bridge a gap, with other communities, for example, the energy production ones, and trying to add an algorithm able to reproduce the dynamic connected with a turbine farm, and identify the interaction with the fields around. This to say that the model is used for process studies as well for implementation that can support also economic activities. Another recent application is connected with the 3D Lagrangian simulation, addressing macroplastic development in the full basin, but considering the rivers and the coastal areas as source and sinks. Next slide, please. Here again, the application that I mentioned on salt intrusion investigation. This is interesting because allow us to identify also what are the bottlenecks in trying to reproduce the full river sea system with the coastal areas, and I will mention it in a minute. And I want to mention strongly the effort in operational modeling that probably was the starting point for SHIFEM. So trying to address the high tides problem that are happening in the Venice Lagoon, and that are a threat for the Venice city. In this year, many development also connected with the use of Earth observation, assimilation data, and new algorithms was developed. Next slide. Bottlenecks and challenges. We have bottlenecks coming from outside the model. So let's say if we want to simulate an environment, we need to have updated bathymetry, have reliable morphology, have reliable forcing, and this is something that probably all of you are experiencing, as well some internal tool technical bottlenecks or challenges that push us in developing new aspects of the models. Just to mention one, the possibility to develop properly the wetting and dry in sigma coordinates, so important for the river branches simulation, as well as reduce the computational cost in order to use this model really also for climate change implementation or for high resolution implementations. But all of these are driven by new scientific question, and now I mention one that could be of interest connected with the compound flooding. So trying to take into consideration what's coming from inland and what's coming from offshore in stressing and putting pressure over the river sea systems. These need a development from a technical point of view, trying to learn from models that were focused for specific issues like flood business models, or try to learn and introduce empirical formulation usually used for flooding in these tools. Next slide. And on these important points that I would like to discuss with you in the next hour are how to do the coupling to take into consideration everything coming from inland, so the groundwater sources and the catchment models, fully coupling them, and how to develop some of the modules of our tools in order to fully address the physics, but not only of the processes that we are studying. That's all from my side.
Thanks, Deborah. So we'd like to introduce the next speaker, Giorgio Silayos from the DUT.
Hello. Hello.
Yes, hello.
Okay. Hello. I'm Giorgos Sileos. I'm a professor in Demokritos University of Thrace in northern Greece. And together with my colleagues from Fisheries Research Institute in Nea Peramos in Kavala, I will present to you a sample of the work we are doing, which will be completely different to what it was presented earlier. So it refers to a coupled hydraulic and fish habitat modeling in the area of a river which is severely affected after the damming of the river. It's the lower Nestos River in northern Greece. So let's move to the next slide, please. So according to the Water Framework Directive, it is presently well known that there are water bodies which are considered as heavily modified water bodies, and these include mostly river systems that have been dammed for several reasons, mostly for hydropower, for the provision of water for agriculture or for irrigation. And all this requires the assessment of the minimum environmental flow requirement, which is a definition that should be reconsidered, especially under the conditions of climate change, the conditions of severe droughts, extended periods of heat waves, and the overall water deficiency. So I would say that according to the Brisbane Declaration, this minimum environmental flow requirement for rivers is defined as the minimum quantity, the time availability, and the quality that river runoff should have in order to ensure the protection of the internal and the transitional ecosystems, as well as the sustainable presence and development of humans whose activities depend on this ecosystem, obviously. So I would say that there is a clear need to go back to the previously defined environmental flow requirements, especially in areas like the lower parts of Nestos River, and reconsider all this under the new frameworks of climate change, as explained, which will, of course, induce significant pressure in the management and in the use of water. The next slide, please. So this is the area of interest. We are speaking about the transboundary water basin, which is shared between Bulgaria and Greece. It's an area that more or less half of the water basin belongs to Bulgaria and the other half in Greece. But as the river enters Greece, there were constructed two big hydropower dams, one called Thissavros and the other Platanovrysi. And there was a third dam over here at the very close at the river delta that was built for irrigation purposes for the farmers of the deltaic part, and this is built since 1960s. So the whole system has three dams that control river flow, and we worked at the downstream part, which is the area that we have significant influence and impact and pressure in terms of water uses and water management. So I would say that we tried really to implement a coupled hydraulic and fish habitat model in the lower Nestos River under various low flow conditions. These low flow conditions represent conditions that are very close to the minimum requirements of that the hydropower company has set for the for its after the construction of these dams, and this was set to 6 cubic meters per second, which is considered really low. So we wanted really to redefine the whole process and see whether this will affect the habitats. We implemented a model which is an open source. It's called River2D. It's a two-dimensional depth average hydrodynamic and fish habitat model, which is widely used in these environmental flow requirement assessment studies. We studied 4 different fish species after extensive sampling in the area: Albunoides and Stremonicus, Barbus tumicae, Rhodeus amarus, and Scolis orpheus. And we divided these fish species in 2 age groups, the adults and the juveniles, and we forced the model under 5 typical low flow conditions. The novelty of this work is that it illustrates that the ecohydraulic modeling of river basins should be considered as an important tool in order to allow us the better implementation, the sustainable implementation of WFP. The next slide, please. So the model results, firstly, let me say that River2D calculates the weighted usable area, and this is based on a sum of composite suitability index. The composite suitability index ranges from 0 to 1, and it's estimated at each point of the computational grid. All the examined fish species showed that an increase in their WUA, which is the weighted usable area, as a result of an increase of the river discharge. So the juveniles were the more sensitive population to changes in the river flows. Overall, the ecohydraulic model results illustrated that higher river flows could improve the quality and quantity of fish habitats in the river, while lower river flows may stress it. So you see a diagram here which shows that exactly how the area, the weighted usable area of a specific species changes with the variance in the river discharge. Next slide, please. I will say that obviously we need to improve, because in modeling the work never ends. We need to have a better digital elevation model, because the area is very dynamic. After the transfer of sediments from the dammed rivers, the downstream part, we need to better understand better knowledge of the suitability indices per parameter. And we need to have a better definition of the upstream boundary conditions, especially now we are in close collaboration with the end user there, which is the hydropower company. So we are now deploying a series of operational real-time stations in order to run the models operational. And finally, next slide, please. I would say a few conclusions that in lower Nestos, the increase of the base flow from 7 to 10 cubic meters per second would potentially increase the habitat area for all species. We estimate that juveniles will increase by 8.8% and adults by 15.3%. Squalis orpheus is the most sensitive species. These are species that are bioindicators for the area, especially under WFT. And the application of this model in heavily modified water bodies could be a valuable tool in evaluating the impact of low flow in these populations in order to assess the minimum flow requirements in dammed rivers. The future work is the installation, as I said, of metrohydraulic stations equipped with an underwater camera with a motion sensor to assess fish behavior under variable river flow conditions. Thank you.
Thank you very much, Georgios. In the interest of time, I'd like to move on quite quickly, and if I could just ask the speakers to try as much as possible to stick to time, which is 5 minutes. Our next speaker is Jebe van der Werf from Deltaris. Jebe, over to you.
Yes, I hope you can all hear me.
Yes, we can.
Yes, that's great. So Nice to be able to talk to you now. So my name is Jebbe, and I present this work with a lot of colleagues of mine at Deltares, some of which are listed here, but also colleagues from Belgium especially. And I will present a very short overview of a modeling of sediment dynamics and morphodynamics of the estuary in the Scheldt River at the border of the Netherlands and Belgium. Next slide, please. So just a very brief introduction to the Scheldt estuary. So it lies at the border of, as I said, Netherlands and Belgium. It's a very important entrance to the harbor of Antwerp, which you see in middle right. And in total, it consists of, you could say, 4 different elements. You have the mouth area, which is at the sea, affected by waves. Then you have the Western Scheldt, which is the Dutch part of the estuary, up to the border. And then you have the Sea Scheldt, which is kind of a tidal river of about 100 kilometers. It's a well-mixed estuary, tide dominant, because the average river discharge of the river is kind of small, 100 cube per second, and the tidal amplitude is ranging from a couple of meters to about 5 meters near Antwerp. Next slide, please. So what we do at Deltares and also at other institutes, we develop and apply numerical models, and we hope that it contributes to policy and management. And in the Scheldt estuary, the policy and management is dedicated to serve 3 functions, which you can show on the left. It's the safety against flooding, it's the nature values, and it's a navigation to especially the harbor of Antwerp. And it's very interesting because those functions are sometimes conflicting, and also there's a debate sometimes between the Netherlands and Belgium, which value these functions different. For example, the navigation is kind of the most important for Belgium, while safety against flooding is very important for the Netherlands because, well, it's crossing at the border, the river. And in this context, it's also nice to know a little bit about the history, because the Scheldt River was kind of controlled and partly blocked by the Dutch 200 years. It's a long time ago, but there's still it's still ongoing, this feeding a bit. So it was blocked between the end of the 16th century and the end of the 18th century. So yeah, that's still an interesting debate going on. Next slide, please. So the challenges are huge here. I think we have we're facing complex physics. We have sand and mud. We have tides, winds, and waves. So we have a lot of forcing mechanisms, and we have obviously the transition from fresh to salt water. And below you can see where you can find mud, and that's typically the intertidal areas, but sometimes also at abandoned channels. It's a large domain, so it's talking about 100 and more kilometers. And well, the questions that come to us deal with long time scales. So they want to know things like, what does sea level rise do, for example? But then you need to model tens or maybe 100 of years. And also the spatial resolution that's required at the beaches, in the mouth, but also at the intertidal areas is about 10 meters. So that's a difficult task. Next slide, please. Thank you. So currently what we do is we have a kind of a traditional approach. We use different types of models. We have like a suite of maybe 5 or even more models. And one of those models, which I show here, you could say it's like the mother model. It's the NEFA model, it's a depth average Del3D model, and you can read in the paper if you want more about it. But it covers the whole estuary all the way to Ghent. And in blue you see the wave grid, and in gray behind you see the flow grid. And on the right, you see that the model is kind of well capable of predicting tidal propagation, and also the phase of the M2 tide is well covered by the model. And we use this model to answer questions on large-scale hydromorphodynamics. So, for example, what is the effect of sea level rise on tidal propagation? Next slide, please. Another example is more focused around at sea, around the harbor of Zeebrugge. I think I cannot point to you, but it's like the coordinate is 0, x coordinate is 0, and the y coordinate is like 375. There you have the harbor of Zeebrugge. And of course, you have these navigation channels running towards Zeebrugge harbor, and they have to be maintained. So we have questions about, well, how can we reduce maintenance of the harbor and the navigation channels? And for that purpose, we need to model really also the fine sediments, and we have developed a 3D detailed model. So it's only covering the area around Zeebrugge. You can see the grid there, so it doesn't run all the way to Ghent. And also, well, it needs to be 3D to resolve, for example, the vertical circulations. Some results are plotted on the right, where you can see the predicted turbidity or the suspended SPM concentrations. And below is you can see the satellite image. So this is the measured SPM in the summer left, and in winter on the right column. So you see the ETM around Zeebrugge in red, and the model reproduces that kind of okay in the top figures. Next slide, please. So this is my final slide. I hope I'm still on time. But future modeling, well, it's kind of addressing the challenges I mentioned before, and what could help very nicely, I think, is like a flexible mesh modeling. We can now do at Deltares for a couple of years with our own in-house FM model. That allows us to have like an easy local refining and faster computations. I included an example of Westerschelde at Walsorde. So there we go from a rectangular grid in 3 steps to a local triangular grid with a high resolution to really resolve intertidal areas. Another item on my wish list, at least, is to have like a fully coupled long-term and large-scale sand mud morphodynamic model. So that's a whole mouthful, but it's also very complicated. Usually we have now a separated mud model and a separated sand model, and we predict different things with that, but that should be integrated, and that hopefully we can manage that in the future. That's it. Thank you.
Brilliant. Thank you very much, Jeppe. I would like to introduce our next speaker, Agustin Sanchez Aquila from UPC. Agustin.
Yeah, good morning. Can you hear me?
Perfectly well.
All right. I'm going to talk about the use for a couple and nested or variable mesh and how we apply them to manage risk or to better tune nature-based solutions. We have basically 2 cases. In the upper picture, you see a bay in the Ebro Delta, south of Barcelona, and in the lower picture, you see one of the beaches near Barcelona. So I'll be talking about those cases, the limits of simulations, and a bit about the challenges for future work. Next slide, please. All right, regarding the beaches of Barcelona, one of the main difficulties we found is how to make sure that the bathymetry is up to date, so that, for instance, after a storm, the bathymetry is correct. We've seen that the errors introduced by a poorly specified bathymetry introduces very large errors. Even more so when we are running waves and storm searches for an increased mean sea level due to global warming, as you see in the lower picture on your left-hand side, which indicates that the shoreline would go through the lower districts of Barcelona. We've seen that those predictions, we have many implications for the owners of those buildings, need an accurate bathymetry. Next slide, please. Also, we found that the models perform reasonably well for, well, this is quite obvious, but let me say it anyway, for the conditions for which they've been validated. Under extreme events, like for instance, a storm we had last January this year, I mean, which is not very large compared to storms in the Atlantic or in the North Sea, but it's quite large, quite exceptional for the Mediterranean. The models did not perform so well. For instance, in the lower 2 pictures, you see there's a sort of siltation or clogging of one of the small craft harbors that we have in our coast. The models failed to produce that. The position is not well reproduced. And in the upper picture, you see on the left-hand side how a coastal pier was destroyed. The model also failed to predict that. And the amount of overtopping that you see in the upper picture, right-hand side, was also severely underestimated. So we have investigated and attribute that limit in model performance to the non-linear character of the wave-induced pressures or wave-induced overtopping or sediment transport. Next slide, please. We have also been analyzing how the bathymetry and the resolution affects the obtained errors, so in other words, uncertainty. And we've seen and quantified for our piece of coast, of course, that by increasing resolution, unless those results that you have in the lower left-hand side table show that by increasing resolution for 100 meters to 10 meters, that is in a structured mesh, the error goes up, unless we fine-tune the closure submodels, the parameterizations, and the interactions. So that indicates that by increasing resolution without doing anything else, the error is inversely proportional to the spatial mesh and directly proportional to the, let's say, time horizon for the prediction. That's quite obvious, but it was good to check that because some of the, we have plugged this, let's say, this suite of models into an operational service from a local meteor service, and they found it hard to believe that by increasing resolution, the results wouldn't get better. In addition, we have seen that there are many unaccounted for errors due to smoothing, interpolation, and particularly when there is a gradient response. So within an impulsive storm event, the errors grow up, or when there is a beach and a breakwater or a jetty, in those gradient regions, the error gets larger. Next slide, please. For another application, that is Bay in the Ebro Delta, we have tested the performance of the models. In this case, it's a circulation model, ROMS coupled to WAM, to SWAN for waves, and to WRF for wind. And what we are analyzing is the renovation time, so the circulation pattern inside that bay with and without land discharges. The two yellow arrows that you see in the lower part of the picture indicate the two main land discharges. And what we are trying to do is to provide advice, guidance to the irrigation people, to the farmers, so that they discharge a bit more water, which is a scarce commodity in Southern Europe, with favorable wind events, and helping them to define what is a favorable wind event for water renovation. It is a very small bay. Maximum water depth is about 4 meters. The entrance at the mouth is about 1 kilometer. So we need a very high resolution simulation to account for that. Next slide, please. Basically, this picture shows that by imposing those land discharges under favorable wind event, and that basically means wind from the northwest, is the typical Mistral wind event, but channeled in this case from the northwest because of the Ebro River Valley instead of being from the northeast-northwest. We reduce the local flushing time using a Lagrangian model from, let's say, 15 days to 5 days, so by a factor 3. So it does work, provided we have a wind which is strong enough and lasts enough to mobilize the water circulation. And that is the main critical point, that those wind events with that strength do not usually have enough strength, enough duration to perform that natural circulation. And because of that, we're also considering small openings in the frontier barrier beach to enhance overwash. And we have also added overwash to the simulations. I will not show that in here. That was shown in Venice in the Eurolag conference last January. Next one, please. And finally, since I only had 5 minutes, 2 or 3 remarks regarding future work. One, that as I see, though I joined late because my computer went down, it sort of crashed. I think that if we have a good bathymetry, using an unstructured mesh is really an asset for improving the quality of the simulations. However, I would say if our bathymetry is not reliable enough or up-to-date enough, maybe the benefit of an unstructured mesh remains somehow hidden. Second one is that we need not only point data to validate the results, as we've been doing traditionally, but also use the new satellite data, for instance, from the Sentinel family, to also reproduce or assess that the spatial structure of the circulation or of the wave field in those very restricted coastal domain is according to the observations. And also, as I said, that we've seen that there are limits in models and data, the two of them. For instance, when measuring small waves inside those bays, the observational data cannot be neglected, particularly regarding wave direction. On many occasions, we tend to smooth the data from the buoys or from the acoustic Doppler profilers and just end up with an average direction or things like that. that introduces a far from negligible error. Same thing regarding the nonlinear coupling effects on your prediction. When your prediction horizon is after 3 days, we found out that then the quality of the simulations, regardless of the model, is not good enough for decision making. And the final picture that you can see here, that's the result from a European project called Curai, where some of you also participated, and it has served to show to our local users, and now they're using that, that Sentinel-2 images can be used routinely to assess the erosion and evolution patterns in areas such as small as the mouth of the Ebro River. And that's all for me. Thank you.
Thank you very much, Agustin. Our next speaker is Isa Sahili from the BAW.
Yes, thank you, Björn. My name is Isa Sahili from the Federal Waterways Engineering and Research Institute in Hamburg, Germany. And my colleague Julia Bendorf asked me if I could say some words concerning the data format that we are now using at BAW in the DANUBIUS RE Modeling Node webinar. So if you are working in, thank you. Next slide, yeah, yes. If you are working, for example, in some predictive institution like BAW and collaborating using unstructured grid and collaborating with other institutions, the issue of data format and uniformization of data format is become very quickly very important. So we made last year some progress in the direction of using NetCDF, CF NetCDF format with UGrid extension for unstructured grid. And I would like to show you the benefits of using such kind of new extension. Next slide, please. So why using the UGrid NetCDF? Because we need a format that is a cross-platform standard, which is safe, robust, and flexible. And NetCDF is there. It's freely available, and you just need to take the libraries and install them and use them. The other issue is the existence of the metadata, the climate and forecast, the very known CF conventions that allow you a kind of standardization of your data. And from that start point, we move towards UGrid, which means the extension of such kind of CF metadata to deal with unstructured grid. Our goal was to use such a kind of extension throughout all the parts of the simulation, from pre-processing to simulation itself, to the results as a synoptic results for visualization, or the post-processing, which is very important for us, the uniformization of post-processing, making some aggregation analysis, making some differences between the different model results or other results from other institutions, and visualize that such kind of post-processed results. So next slide, please. Why are we using UGrid NetCDF again? Because it's there, of course, and you have, first of all, the safe use of dimensional data. So the data are not only stored as numbers, but you have also the units, the canonical SI units there. So this is, of course, very important for the safety of your data. You can also perform data transformation, for example, from intensive variables to extensive ones. For that, you have for example, the attribute cell methods, which express the correct significance of data, if they are point data or main data of a cell, or any kind of integrals over a space or time. And if you link it, for example, to a cell measure, you can perform conversion of data from, for example, intensive to extensive variables at the post-processing level. So you don't need to rewrite your code. everything is done in a generic fashion at the process at your post-processing step. You can also make some filtering of your data based on some, let's see, some numbers. So you can perform a very easy title analysis during the post-processing. And for that, you can use, for example, such kind of CF ancillary variables, which link your original variables to other ones in order to make some filtering. I will show an example later on that possibility. And of course, you can keep track of your data processing. This is also a known issue in NetCDF. So you have the attribute history, and you can see everything you did or which modification were performed on the original data. So you keep track on all the modification that these kind of data experienced during processing, from pre-processing to the visualization. And of course, you have to adapt your visualization tool to deal with such kind of UGrid NetCDF results. Next slide, please. So I will just move exactly to some examples. This is what you see here is a flow chart of the German byte operational model called GBOOM. This is a model involving indeed two models. The first one at the boundary side, which is forcing from the Dutch continental shelf model, flexible mesh, kindly provided by the Taurus. This is that we are using such kind of model for forcing. This model is also using UGrid NetCDF as a grid and also as a result. So the results, the UGrid NetCDF results from the DFlow-FM DCSM model can be visualized as is from our post-processors. They can be also processed from our post-processor, and we use them as synaptic outputs to force our operational model every day. The operational model is using UGrid NetCDF on all the parts of the simulation, also for initial value and for the grid itself and for the outputs, on location, on some sections or on area. And as I said before, this kind of synaptic results will be analyzed with our post-processor without any modification. So what I want to say is that UGrid NetCDF is present all over this such kind of coupling, and both models are dealing with one another without any problem, just because they are using the same standards and they can understand each other without any kind of modification, even at the post-processing level. Next slide, please. So from this model, I will show you exactly this kind of result. This is the mouth of the estuary Elbe. I think you saw some pictures previously in the previous talks on this area. And this is the tidal characteristic number of water level. So there are kind of 28 tides which are analyzed from February, March last year exactly. And what you see here is the mean tidal low water during this period. And you see the use of such kind of attributes, cell methods. The period is a mean value for these 28 tides. And the phase, of course, is mean, which means you have a value for every polygon. And through using the use of ancillary variables, you can link this kind of results to another variable, which is the number of observation. And using the number of observation, you can filter your tidal mean water according to what you want to see. If you want to see all the location where all events were detected, or to see only a location where a certain number of observations were detected, and so on. So there's a very you can do such a kind of analysis in a very flexible way at post-processing level. You don't need to write anything new in your code or in your post-processors. Next slide, please. So what were the challenges for the implementation of such kind of new technique? So of course, the implementation of the U-grid methods was very challenging because those are methods that should be implemented at low level in a generic way. And throughout the implementation of such kind of methods, you will of course encounter compatibility issue. I think everyone here in this group knows what the problem is. The compatibility issues from some other prerequisite libraries like HDA5, which stands behind the NetCDF4 library, or the solvers like the PETSI solver and so on. So those are problems that should need to be solved also in a generic way. What we are, this is very important here, what's now is an ongoing project between Deltares and BAW is to try to enhance the DFlow-FM. The DFlow-FM is a new modeling system for using flexible mesh in Deltares under development. And we are now collaborating with Deltares to enhance the output of DFlow-FM so we can use them directly, plug them out directly in our post processors and process them, visualize them, and so on. We have some results, so we are now able to perform such a kind of a direct processing of DFlow-FM results with our NetCDF post processors. And we would like, of course, to make such kind of extension, the U-grid extension, as a full part of the NetCDF CF conventions. So if they are accepted, there would be a kind of worldwide standard. Of course, there is also the need to perform the backward compatibility between our results and the results of DFlow-FM. This means use our results in the other way for DFlow-FM, for forcing DFlow-FM, or for the post-processor of DFlow-FM. Next slide, please. I think this is the last slide, exactly. So now we have the U-grid NetCDF implemented in Antrim, and it's also implemented in DFlow-FM or DELF3D FM. And we are still open for others to enter such kind of collaboration in order to establish the U-grid NetCDF format as a widely used standard for exchanging data and for processing unstructured model results. And yeah, that's it. I would be happy to answer some question afterwards.
Thank you very much, Isa. In the interest of time, I'm going to move on to the next speaker, Julia Bendorf, also from the BAW.
Yes, thank you very much. Isa already made kind of a good introduction to the next topic, which is the importance of post-processing of modeling data. And I will shortly talk a little bit about tidal, harmonic and long-term analysis, and also aggregation, and why we think that these topics are very important to discuss here in this community. Next slide, please. Yes, this figure is unfortunately in German, but it doesn't really matter because you don't need to understand all the words. It shows the characteristics of the current velocity during a tidal cycle. And I would just like to point out that there are a lot of parameters to consider, and I will come back to that later. But in order to talk about the results of numerical models, we need to be able to process these results in a way that we can transport them to a public and communicate the results. And for that, we need a common understanding of all these different parameters. Next slide, please. Yes, here we have a little table of some possibilities of analysis. These parameter list, of course, is not complete, especially as we heard before, there are coupling of models with, for example, water quality models. These are not included here, but this is just to illustrate what I'm talking about. So after we have the numerical model run, we do an analysis of the data. And this is part of the post-processing, of course. And each parameter, yes, next, please. like for example the water level, can be analyzed, for example, according to the tidal cycle. Here we have, for example, the mean tidal range over a certain amount of time, for example, 2 weeks, like one spring neap cycle. And next, please, is the flood to ebb current duration, which is also a tidal analysis, but of the current velocity. And next, please, we can also do a long-term analysis. For example, in this case, the duration of high SSC values during some period of time, not necessarily, but also possibly in a tidal area. And yes. And in addition, of course, there are the harmonic analysis, which is often used, but also transport analysis for certain parameters. Next, please. Another possibility of post-processing is, for example, the aggregation of data in certain spatial control volumes. Here, for example, we have the water volume flux between these control volumes, which is also a nice way of aggregating the data and showing certain results in a simplified way. Next, please. And so what is now the problem with all of this? We all use certain characteristic values in order to better understand our models and the results, and also evaluate and visualize them. But we are never 100% sure whether we are speaking of the same thing when we talk to each other. For example, the duration of an ebb current, does it last from high water to low water, or from flood slack to ebb slack? So I've already, for example, had this problem in a discussion, and in the end we found out that we were talking about different things. And therefore the choice of an adequate analysis time and reference points is important, but also for the communication of results, we need to have some kind of common understanding and be able to compare different methods. Yes, next, please. And therefore, we propose to work on these topics together within the modeling community in order to develop standards and work on the validation and quality control of these post-processing methods, because post-processing is essential for the communication of results. I think in one of the talks before, it was mentioned the communication with the authorities, for example, and it does not, this post-processing does not only consist of making pretty pictures that are colorful and look nice, but it also needs an elaborate and high quality post-processing methods that ideally are understood by the whole community. And yes, that was my talk. Thank you very much for your attention, and I'm very much looking forward to the discussion.
Thank you, Julia. Our next presentation is by Donato Kanu. Handing over to you. Donato, can you hear it? You might be muted. We can't. Ah, there we go. I heard something. No, hang on. For some reason.
Can you hear me now?
Yes, we can.
Okay. Probably we were unmuting together, so we were muting again. Okay. So hello everybody. I'm Donata Kanu from the National Institute of Oceanography and Applied Geophysics in Italy. In this slide talk, I will present a modeling application focused on the mercury dynamics in lagoons. That was done with colleagues, coupling the SHIFEM, shallow water finite element model presented before by Deborah, with MERC, that is a routine simulating mercury dynamics in water environment, extracted from the water analysis simulation program from the Environmental Protection Agency of USA. Next, please. So, why mercury? Mercury is a pollutant of concern because it's toxic in its methylated form. It also can be accumulated in the trophic chain and enter from the trophic chain to the human diet in humans. So this is why mercury. Moreover, mercury is present in hotspots in the Mediterranean and the Black Sea. Therefore, it can be a pollutant of interest in the DANUBIUS research infrastructure. Moreover, monitoring and measuring mercury is challenging. It costs a lot, and it also needs specific monitoring, sampling abilities. And that is why integrating models with the measurements can support the evaluation of the mercury contamination state in the systems. Next, please. Okay, so the objective of this activity was therefore coupling high-resolution finite element model applied to the Venice Lagoon, which is one of the lagoons located in the North Adriatic area. That is one of our research areas in Danubius with the mercury model. Mercury module was used to simulate the fate and transformation of mercury in water and in sediment. These modules enables us to follow the transformation that are microbially mediated, and also transformations such as photooxidation, reduction, that transform mercury from its oxidized, reducted, and methylated forms, and also following its partition in water and in sediment. In the other way, SHIFEM was used to simulate its transport in the waters, and using a simple model, a simple sediment transport to module, we also aim to simulate the transport of mercury in the sediment compartment. This was done using partition coefficients between of mercury species in water and in sediment. The last part of the activity that was done in the last months was also linking mercury to the biogeochemistry of the lagoon, but this is something that is still going on, so I'm not going to present it. But the novelty of this approach is to model in a high resolution process that deals with a toxic species and biochemicals, and up to the biological processes in a river, lagoon, sea system. Next, please. Next, please. I'm ready. So, which are the yes? I don't remember. Back, please.
Sorry.
In brief, in the left side, we can see a map showing the mercury in water, the total mercury in water, and in comparison with the data, we see that matching with the data is not so good up to now. So we are still working on the parameterization. Parameters are being taken from the literature and using also parameters measured in lab. In the central part, we see mercury concentration in water compared to the data, and the right side we see the simple model that was used to simulate the suspended particulate matter, and compared also with the data. Next, please. Here we see the concentration of silt in the lagoon bottom, and mercury in its mercury 2 in the seabed, and methyl mercury again in the bottom of the lagoon. Next, please. And so we had some challenge to overcome, that were selecting a sediment model that could be useful but enough simple to be coupled with the mercury, and so manageable at this stage of our work. And also we have some challenges that were due to limited data availability for mercury species, in particular for methyl mercury concentration, and to uncertainty in the mercury cycle. Another bottleneck is the computational cost. This application takes quite a long time, 6 days for 1 year, so it's quite costly. Next, please. And regarding the future work, we aim to improve the coupling with biological processes, and increasing and improving the representation of some process, like introducing particular organic matter remineralization, and the link with the mercury dynamics. We aim to add also the bioaccumulation processes in phytoplankton, and the dynamic. Another possible improvement can be the coupling the model with the dynamically with the atmosphere. Of course, also improving the linkages between the lagoon and the riverine system can be an improvement, and as I said before, the sediment module can also be improving the sediment module and making it more representative of the reality. Also can be a significant improvement to the work. Thank you. I think that's all.
Brilliant, Donata. Thank you very much. Our final speaker today is Jens Wöhrer from the German Federal Institute of Hydrology. Jens, over to you.
Hi, it's me from Koblenz. I would like to share a few experience with water quality model we made at the Federal Institute of Hydrology. Please give me the next slide. We do develop the QSIM model since meanwhile over 4 decades, and the question behind our investigations was always, the main question were oxygen deficits. And on the left you see a a map of Germany and which part of Germany belongs to which catchment area. The blue lines that cross the catchment boundaries are canals we do not work on. A deterministic, well, and meanwhile we have modeled nearly every river in Germany and every estuary. A deterministic model that wants to find out about oxygen deficits is has two main components, and that are the buildup of organic carbon by algae or other plants, and the mineralization of organic carbon to carbon dioxide by bacteria. So you have to model the carbon cycle with this. And if you want to know about algae, you need to have to model their consumers. There's a second trophic level. You have to know about nutrients that might be limiting. So the consumption is limiting on primary production. The nutrients might be limiting on primary production. And you have to model a few physical things like temperature, light, and surface aeration. Well, this in brief only to point out why we think our model is specific for larger German rivers. We are modeling algae as primary production. We model some special species, for example, mussels as benthic feeders as for consumption. Next slide, please. Here is you see a map of the Elbe estuary on the left, and Johanna already introduced to you the oxygen deficit in the Elbe. And if you see this this Elbe estuary colored by the age, the water age, so the time that that went until the water entered the estuary, then you see the oxygen deficit is where the water is around 1 week old. So it takes the organisms 1 week to develop this this oxygen deficit, and not shown here is a river model, a 1D river model that that computes the buildup of this organic biomass, and that takes also around the organic biomass causing the oxygen deficits takes also around 1 week. So what is specific about QSIM? We have the experience with the climate conditions in Germany. We modeled freshwater, and we have, well, somewhat longer retention times. Next slide, please. The second larger topic here is software engineering, let's say it this way. We do run a 1D branch and a 3D branch of our model. We drive them by different hydraulic drivers. Hydrax is a 1D driver, Antrim, Schism, or Maikazu are multidimensional drivers, and we do an offline or soft coupling. I think it was already by Thomas Brody called external coupling, but maybe we can discuss that later. And the metabolism, the biological components are the same for both branches. And what is specific for us is that we steer all this model family biographical user interface, which is not for our experience, is not only for efficiency, it is also for safe model build up, for reproducible research, to do archivation with this, and to have a quick look into the model results, which is much more convenient if you have a graphical user interface. Next slide, please. Well, I think this is already the last, and the challenges I see. Yes, that's the right slide. What I think I was able to introduce to you a little bit is that water quality simulations need large model areas because organisms need time to develop, and you need integrated models to have all the components, the biology and the hydrology modeled. What I do think as Danubius tries to give not only software and hardware facilities to researchers, but also the possibility to get expertise. Then I think the interdisciplinary expertise that is used, for example, for water quality modeling, to link to this interdisciplinary expertise might be challenging. Format standardization, as Isa already introduced, the example with the Elbe was based on BAV computations handed over with in UNTREM format. I would like to pose the question if more than only post-processing should be addressed in working group 3. And to comment on working group topic 4, that biological and water quality simulations are clearly more site-specific than physical ones. Thanks for listening, and I'm looking forward for the discussion.
Great, thank you very much. We have scheduled, so you may have realized we've run severely over time. What I would propose, we had put in time for a break and an hour-long discussion. We have booked the studio until 1 o'clock Central European time or Delft time. So we do have time for the discussions, so don't worry that we're not going to end at 12, we'll carry on. What I would propose now, before we start the open discussion and the questions, as we go for a 5-minute comfort break, and I'll update the slide in the meantime. Great. Okay, we'll be back in 5 minutes. Okay. Great. Hello, everybody. So it's 11:45 now, and we're back. We've got about an hour's time for an open discussion. Before we go there, we have got a number of comments and questions that were posed during the presentations. And first of all, I would like to thank all of the speakers for spending the time and giving the presentations. Thank you very much. They were all very excellent. We have a question for Thomas Brudi, if he's still here. The question was from Bert Jagers, and the question is, what do you mean by external coupling? File-based coupling or via API? What technology do you expect to use?
Yes, but in my opinion, both ways of coupling will be possible. It's not yet discussed or decided which way of coupling. It's only a spatial coupling. So in the Telemac code which we are using, an API is possible, a coupling via API, but it's not decided yet. But in my opinion, I think the best way in this spatial coupling will be to have continuous models, because the external coupling always is connected with some losses of information. So I would prefer the continuous modeling.
Great, thanks. Thanks for that answer, Thomas. Then another question for Aisa Sahili on the NetCDF CF conventions. It was actually a comment rather than a question by Bert Jagers. The latest discussions between the CF and UGrid communities are going in the direction of a formal collaboration and endorsement of UGrid by CF rather than full integration. So this is to bear in mind in your development.
Yes, we will be happy if there is some effort in this direction.
Great stuff. So I would suggest Bert to take up contact with Aisa to discuss this further offline if necessary.
Yes.
Great, thanks for that. Then we have a comment from a PhD student, Josias Nongbe. He says, "Wow, this is exactly what his PhD study is all about." The webinar has answered a whole bunch of questions, but now he also has a whole bunch of other questions, and he would like to get in contact with the Danubius crowd. So Josias, what I suggest you do is you go to the danubiusri.eu website, and I'm sure there you will find all of the contact details of at least somebody that could help you. And I suggest that is the route you contact them. Alternatively, please feel free to contact the organizing committee of this webinar, and we will put you in touch with the relevant people. Then and I suggest you talk to, and then another comment from Josias was about getting links to NetCDF in applications of modeling, and Josias, I suggest you contact Aisa for that. Helena van der Wecht asks, a number of talks mentioned creating standards in, for example, output and post-processing. Is there also an action plan in getting these standards widely adopted? Are you linking the proposed post-processing methods to specific types of questions? For example, this type of question is best answered with this standard analysis. Does anybody from the panel want to tackle this question?
Please go ahead.
Yes, sorry. I think this is a very good question, because it brings us to the origins, and what we want to have is only one standard, one standard used for all over the different parts of the simulation, for the mesh, for the initial conditions, for the forcing, for the synoptic results, and for the post-processing itself, for the aggregation, for the analysis, for differences, and for the visualization and making some statistics. So this is the basic idea, to use only one standard for all these steps. So we don't need to modify anything, and the flexibility and robustness of such kind of methods is the possibility to make analysis or make modification or perform any kind of transformation at post-processing level. So you don't need to touch any line of your code, simulation code, or your of your post-processor. And this is our what we are striving for. So we made, I think we are, we made a nice job at BAW in collaboration with Deltares. And what we hope is that this kind of standards now became step for step widely used. As for the acceptance in the CF convention, it will be, of course, a very long way, but I think if there's such kind of methods are step by step widely used, I think we will get there in the CF metadata conventions somewhere. Yeah.
Lovely, thanks, Isa. I'm sure you will.
And maybe I can maybe
Yeah,
I can add
Julia,
a few words. Thank you. Maybe I can add a few words about the post-processing part, because I think this question exactly, yeah, covers what my question would be for this working group. Like the questions that should be tackled there are exactly those of how can you standardize these methods, and what is a good way to start. And so that's exactly what we're looking for, actually.
So I would also comment on what Isa was saying. I think it's an incredible and very important point that he raised, the standardization of formats. And I fully back this. I think it would bring our community further ahead, especially with the fact that NetCDF unstructured formats are still widely not used, and adopting a standard for the unstructured grids would be great. And I think not only that it's important that we have this working group inside the modeling node, but we should also think about using DANUBIUS, using the European research infrastructure, and hopefully later the ERIC that we are building, in order to push this kind of standard also into other institutions. And we should think about using the DANUBIUS name and the DANUBIUS infrastructure in order to, how could I say, try to make this clear to these commissions, in order that we completely back this idea. And we would like to see this kind of standardization also inside the CF conventions.
Thank you, Georg.
Can I just add one thing?
Yes, absolutely.
I think there is an action connected with the standards on data, but as well on the analysis. But we should think that we as a community can fill a gap or can try to bridge these gaps. So if we are not able to spread a new standard or a new approach fully, one action can be in any case connected with creating the possibility of interoperability. So the possibility to use the available standards or the available data in any case with our tools, because we have to broaden the community and to allow people to join the community. And probably proposing a standard is perfect. Trying also to deal with the complexity of the different approaches and try to make them interoperable is the other action that is needed.
Thank you, Deborah. So for the time being, we don't have any more questions on our questions tool at the moment. So, oh, here, one just popped up as we speak. This is live. Helena asked, I think one standard may not be able to answer all questions. For example, Yeba presented different approaches for different questions. My opinion is that all proposed standards should be question driven. That's a very interesting point of view. Would any anybody from the panel like to respond to that?
Agrees in approach.
I think the problem might be with if you propose a standard per question, then you might have many standards, right? Because we have many questions to ask. So I'm not sure if I understand the question correctly, but I think we could probably learn from the atmospheric or the meteorology communities in terms of standardization of data formats. And certainly when we're moving towards adopting FAIR principles, so findable, accessible, interoperable, reproducible, standards and data formats will certainly be important. If there aren't any further questions at this time, I would suggest moving across to the Mentimeter. We've prepared Mentimeter questions for us, and this was a bit of an icebreaker. So if you go to the audience, if you go to menti.com and enter the code 6686265, you will be able to vote on the various slides that we have. So please, you can do so using your phone or your computer, whichever you prefer. So this was a bit of an icebreaker question. I hope you all enjoyed the talks this morning. I certainly enjoyed them. I personally was quite inspired. I come from an oceanographic background and an open ocean modeling point of view. So it's very interesting to see that similar challenges that I've encountered in ocean modeling are also true in the river and sea system space. So I'm glad to see that many of you have enjoyed yourselves and that you've been inspired. And it seems like most of the things that have been presented here are quite new, but also known to some extent. So that's always great. Fantastic. So if you don't mind, I will move on to the next slide.
Still counting.
Oh, still counting. Maybe I should be less impatient. We were very pleased to see that there were about what was it, 45 attendees for this webinar.
Yeah.
So quite a nice big group of attendees. Thank you very much for your patience while we muscled our way through the technical challenges of having 10 presenters. Okay, so if I move on to the next slide, we now want to collect some information from our audience about who, where, and what. So the first question we have here is just what is your job title? For example, I count myself a researcher, but in reality, I'm probably more of a project manager. And sometimes you are able to give multiple answers. So we have one researcher in the audience. That's great. We have two. Oh, I'm glad to see we have a physical oceanographer in the mix.
Software development.
Software development. That's really critical for these kind of things. PhD students. Okay.
Well, that's a team.
Yeah. Okay, great. Seems like we have a nice distribution of research, science, management, also across disciplines, it seems. Ecology, ecological modelers, particle dispersion, we've got oceanographers, we've got coastal modelers, we have climate scientists, geophysicists. So a very nice distribution of participants. Thank you very much. So the next question is about which river and or sea system are you trying to model? So the DANUBIUS, the speakers gave a nice overview of the systems that they're trying to model and some of the challenges. So it would be interesting to see what systems our audience are trying to model, if any. The North Sea, the Venice Lagoon. Delta. Okay. Lagoons in general. Yeah, interesting. Northern Adriatic. Minho, Lima, and Douro rivers. Where are those? Okay, so a largely European focus,
also
with
Indonesia.
some, with some in the Far East, yeah. Okay.
And the Elbe is popular.
The Elbe is definitely popular, yeah. Oh, here's the Danube, Black Sea as well.
Yeah. Spain.
Is this one Spain?
Yes.
Okay. A disclaimer, I'm from South Africa. That's why my European geography is not that great.
Well, if you look up all these systems,
we will have
all across Europe.
Yeah. So certainly, if there's a big European center focus, there's certainly scope to have almost a European river sea system modeled in place if we can couple everything together, right?
Yeah.
That would be quite simple. Okay, moving on to the next slide. There are, what are your scientific interests? So I've given a couple of categories here. In the next slide, there's going to be a question about what are your other scientific interests? So if you haven't been represented here, don't worry, you'll get a chance in the next slide. Including, okay, so ecology and water quality, hydrodynamics, okay, hydraulics. Hydraulics in this instance is related to dams and that sort of thing, correct? Or that would be what is maybe a question for the panel? What is your understanding of hydraulics in this context of modeling river sea systems?
Structures in this case.
Structural in this case. Okay. Okay. So mostly hydrodynamics. Interesting. A lot of climate change, a lot of sediment transport. And quite a few on relatively less on water quality and pollutants. That's interesting. Those are quite hot topics at the moment.
Well, if you sum them up, there are 12.
Yeah.
Similar to sediment. Yeah.
True. Right. We add them together. That's a good point. Okay. Then, what other scientific interests do you have? Personally, I'm, for example, interested in how to couple coastal ocean models to the more open ocean models, and how to do that in an effective way and a consistent way, at least. Because in the open ocean, we're modeling significantly different scales compared to the coastal ocean, and they typically have different methods in terms of modeling. And yeah. Okay, data management. Data management is an interesting one.
Well, throughout the topics, you see a lot of people working with new data sources.
Yeah.
For instance, investigating what they can do with remote sensing, Earth observation.
Absolutely. That was a question that I had at, I think it was for Agustin. He mentioned the need for a good bathymetry data, because that is a big source of errors when simulating the coastal environment or the nearshore environment after storms. And I was wondering if, Agustin, are you still here, if you've looked into using satellite remote sensing data to derive updated bathymetry in more real time, or if the Danubius community has looked into that at all.
Okay. Still here.
Okay, wow, there's a lot of interest here in, at least it looks like quite a bit of interest in integrated modeling and numerics, and that seems to be the most popular words. Modeling of timescales also seems to be quite a popular one, but there's definitely a broad range of topics here that I'm sure are very interesting for the community in general, and I'm sure there's experts throughout Danubius that can collaborate in these spaces. That's very interesting.
What occurred to me is that several of the speakers are making chains of models.
Yeah.
So they start with a catchment model, and then with a model of the open sea, and on top of that they couple a water quality model and then maybe an ecological model.
Yeah.
And I was wondering how are uncertainties propagating throughout this entire chain of modeling, and if the speakers and the audience have experience with this.
Yeah. Would anybody from the panel like to comment on that? The question was, we're coupling a vast array of different models and at different scales, and how do we deal with gosh, what was the propagation of error in that space? Joanna, perhaps your group can comment from the data simulation point of view. I know their error is also a really big issue in terms of dealing with those sources.
Yeah, of course, errors are big issues, and we all know we're all dealing with errors. Those are errors in the numerical models. Of course, as long as we increase the resolution, there are different processes and they are not well represented. So we try to do our best to tune our models, but nevertheless, due to the uncertainties in forcing, atmospheric and boundary forcing, but also in the parameterization, there are errors in our models. We are all familiar with that, and at the end we have to live with that because there are no perfect solutions. Another errors, however, and we have to have that in mind, is also the errors in the observational data, because not all data are perfect. We try to use as much as possible the availability of the in situ observations, but they also limit another available data at the moment, satellite observations, and fortunately in the past, near past, and nowadays the resolution of satellite observations near coastal areas has been improved. A good example of that is the Sentinel data, but nevertheless, as long as we approach the coast, also the satellite observation is with errors. There are many possibilities of dealing with the errors issues. You mentioned the data assimilation, which is also the latest stage, but normally there is a normal postulation. You don't assimilate wrong data into wrong models, but we have also to make some analysis before that and to make the best use of both models and data. But before going to data assimilation, another method to deal with the error issue is collocation method. And we are working on that. We also develop some tools that we can make it to the DANUBIUS community and scientific community, in which triple and multiple collocation methods have been developed and implemented to set up the errors between if you talk on triple methods, it's between three sources, which are in situ observations, models, and satellite data. Due to that method, of course, you can assess nicely what are the ranges of the errors of your sources, and then using that to make a further step, which are OSSE analysis. OSSE stands for Ocean System Observation Experiments, which also provide a good first guess what is the best place to have measurements and what you can obtain. So it actually is a nice and powerful tool to look for the best places and time for producing measurements in order to improve the model. And then, of course, it is a data assimilation with also different methodology, which is not so trivial as long as we are really working on river and estuary models, and we are using also coupled system, because we also have to talk on coupled data assimilation.
Yeah, and that is challenging indeed. Coupled data assimilation is not easy. I imagine with observing system simulation experiments, or OSSEs, to identify areas where you might need observations, that type of approach might be very sensitive to the model that you're using, right? You might get one answer with one model and another answer with a different model. So those are also quite interesting challenges to overcome in that space. Okay, let's moving on to the models, tools, and software that we're using. So here we have a group of 4 models. Which one are you using? In the next slide, you can list which other models you're using. And I guess we should point out that this is not a competition. Interesting. Okay, so fairly good spread between the different modeling approaches. I always find it very useful to do intermodel comparisons. This is one way where we learn very nicely about some of the pros and cons of the different modeling approaches. Assuming, of course, that you have the same boundary conditions, the same forcing fields, there is a range of things that you need to do intermodal comparisons in an effective way. But it seems we have quite a big group of users of the Deltaris and SciFem. I don't know if I've pronounced that correctly, but perhaps that's also illustrative of the audience. I don't know if we've managed to reach that many people in the other modeling domains. Interesting. Okay, I think most people have voted on this one.
19.
Yeah.
Well, let's have a look at the other systems.
Exactly. That'll be interesting. What other systems are there, in fact?
Let's see.
SSIIM. X-Speech, yeah.
QSIM was in the presentation.
Ah, yeah, we missed QSIM, that's right. Yeah. Yeah, interesting. Okay. And a question, maybe a naive question to the panel: are the modeling softwares that are being listed here, are they significantly different in their methodological approach, or are they quite comparable in how they tackle for example, the shallow water equations? Or
for example, if we compare the Antrim and the new DFLOFM from Deltaris, so they are based on the same semi-implicit method. I think Schism also is using the same original idea from Kazuli, and the only difference is of course, the treatment of the explicit terms, which are kind of Euler-Lagrange in Antrim allowing large time steps, and they are in other systems CFL condition bound.
right.
But mainly they are quite very similar, and I think Schism and DFLOFM are quite similar to Antrim.
I can confirm that also SciFem is using same implicit approach.
Okay.
So
I didn't know. This is new for me, the SciFem. I didn't know. So I learned something today. Yes. Thank you.
Okay.
I can also see some modules that can be or are also coupled with SciFem. For example, BFM.
Yeah.
Or we have the L-trans, that is a Lagrangian particle model that can use hydrodynamic fields computed with hydrodynamic models or computed or from data.
Since we are also talking on software and on integrated system, which is not only hydrodynamics wave, but as you mentioned, coupling with ecosystem model or sediment model, also a part of the software and the system is a coupler. How do you couple the different model systems? Because there are different ways of doing that. The regional community is much more advanced than the river and coastal communities, but one way of doing that is, of course, direct integration of a model, but another more flexible is of doing it via coupler like FABM for ecosystem or chemical model components, or external coupler like Oasis, in which you can couple hydrodynamics with waves and atmosphere. It also belongs at the end of an integrated modeling system.
And maybe what we completely forgot about, at least I forgot to put it in now, I cannot put it in anymore, is kind of modeling of drainage basing, for example, SWOT, I think that a lot of us are also using, or so that should also be added probably to this kind of simulation software.
Good point. Okay, great. There, somebody just added it for us. Thank you. Cool. Okay, great. Thank you very much for that. We had a comment from Bert Jarchus again regarding the error propagation. He says that it depends on what aspect of the results you're interested in. As long as the erroneous intermediate results are still within the natural statistics that you want to represent using the simulation, the effect may be limited. If you want to represent a specific event, then any error will accumulate. Thank you, Bert. Does anybody from the panel want to respond to that? If not, then we can move along. So this is the next question is, what type of data do you use when you set up or implement your model? This could be for initial conditions, for boundary conditions, for forcing. What data do you use? Even for validation, all data. Yeah, exactly. All of the above. Data is an interesting one. So I come from a numerical modeling background, and I used to treat data as the truth. And then I moved across to doing a little bit more data simulation work, and then I realized, well, it's very far from the truth. So there's always that. It's amazing what type of errors you start introducing in your models when you don't really know what you're doing beforehand. Okay, so it's a very even spread. Interestingly, remote sensing data is used the least here, and in situ measurements are used the most. I imagine that to date that has to do with the resolution of the satellite sensors that are available to us. In river sea systems, you need particularly high resolution to resolve the processes of interest, I imagine. So perhaps now with the Sentinel series satellites coming online and being online and the data becoming more available, this ratio might change.
That's also what's available in the remote sensing data.
That's true as well, yeah.
If you're studying some dissolved pollutant.
Yeah, you can only measure the surface, yeah? Yeah. True. Okay. If the panel wants to comment on any of these points, please feel free. So the next question is, where do you get your data? The Copernicus program is a big resource of data, but do you also get data from your national repositories or other national agencies or even international agencies or initiatives? Where would you get your data for your models? National agencies and national repositories. Interesting. eModNet, yeah. Internal repositories. That was so that implies that most of the data is kept internally at the agency that you're working at, and that you use that in your model setups. How do you then deal with reproducibility or making your models fair, for argument's sake?
How open is the data?
Right. Yeah, exactly. And we're moving towards more open data standards, own measurements. Interesting. CMEMS, national repositories, ECMWF. Okay.
Also, how do you store the data in relation to the model?
Yeah.
Do you build up your model time over time from a database, which is the source of origin, or do you keep adjusting your model schematization and you figure out something new?
That's a very good question as well. I'm surprised that is there a central place where you collect digital elevation models, or are these sort of part of national agencies or national repositories? To the panel, I see heads nodding. So okay, so a combination, I imagine, right? You can use the international agencies' digital elevation models, or whatever you collect locally and combine them in some way, right?
Yeah, one of the precious results are that efforts in trying to merge, particularly for bathymetries and topographies, the different sources of data, trying to cover larger areas, and also to obtain storage of updated information, particularly for bathymetry. So having the same area covered in time, for example, with different surveys, and make this data available is something that, at least now in Italy, is not so diffused.
Interesting. Okay.
And the continuous data is something that is really missing.
The time series data to do the validation.
Yeah, not just punctual time series, but having the data in continuous with a good frequency in time, and not only a good resolution in space, is something quite important.
Yeah. And I imagine it's also the funding programs to collect observations typically are, at least in my experience, becoming less and less. There's always less money available for collecting data and more money available to innovate in methods, for argument's sake. So collecting data is becoming a real challenge these days. Okay. I noticed in one of the previous comments there was or one of the previous slides there was a note about data management, and that there's an interest in data management as well. Has the River Sea community or the Danubius community engaged with, for example, the astrophysics or the high energy physics communities? I spent some time working at a company called EGI, where we worked a lot with those communities, and they have done some remarkable things in data management and data standards and leveraging cloud computing technologies. Has Danubius thought about any of that?
No? Well, Danubius has should follow the European initiatives connected with fairness on data. So this is something. This is the pathway. So yes, I think that Danubius has thought about that, but the way is quite long, and comparing the experiences on data and on standards from others is really a long work.
It is absolutely. But there are definitely initiatives in the sort of more IT sectors and the IT research sector that are trying to facilitate that. So it's actually quite useful to engage with those communities, in my experience at least.
But once you have the tool, you have to convince the researcher to align.
That's true too. Researchers, myself included, like to do things their way. Okay. Our next set of questions will be around hot topics, problem solving, and challenges, which is largely also what some of the slides and the presentations were about. So the first question is, what is your main challenge? What are your main challenges and bottlenecks when it comes to modeling river sea systems? I know it's quite a few. So integrated modeling, I imagine connecting the different models, as we were talking about just now, is for sure probably coupling systems, absolutely. And I imagine coupling systems here, you mean coupling different modeling systems, right? If you're going from trying to integrate different models in an integrated approach.
If you look at the pages with the challenges in each presentation, you get a very nice overview of what the main challenges for the modelers and the model developers are right now.
Yeah.
So that's what I enjoyed about the presentations. It also helps the modeling community to get focused on what's important.
Absolutely, and it's interesting to see that a lot of the time we're all dealing with the same problems, right? And if we can get together more regularly, then we may find good ways of overcoming these problems. wetting and drying and sigma, yeah. Computation time, cross-scale approaches, yeah. Calibration of models. Yeah, that also links to, I think, the comment that Jens made about how it seems that you really have to parameterize a lot when you start water quality modeling, and that there's no sort of generic approach that you can implement. Full parallelization.
And Jens also commented that models are site-specific.
Yes, that's
water quality and ecology models are site-specific.
Yeah. Define and set. Benchmarking. Benchmarking, I wonder if you're talking there along the lines of how long it takes a model to run, or if you want to have like for example, a benchmark from an ecosystem point of view, you know, like having a baseline of this is the current state of the ecosystem. I guess the two are valid.
They also use benchmarking to compare several modeling systems with each other.
Yeah.
And that always gives new insights in how the system functions, but also how the softwares and the model are functioning.
Yeah. Lack of data. So that seems to be another challenge. Yeah, lack of continuous data. It's interesting to see that that's also, so I mentioned that I'm from South Africa. A lack of continuous data in South Africa has always been a big challenge, but it's also interesting to see that that's it appears to be a global challenge. So it's interesting as well. Fully coupling different time and spatial scales.
Well, sometimes you use models to fill in the blanks.
Yeah.
There's not enough data.
Yeah.
That can happen as well.
Yeah. I was wondering about the idea. So there was another comment, and I forget now which presentation it was, but it seemed that when you increase the resolution, you actually increase the error as well, because I think you need to parameterize the model as you increase the resolution. Right? So I'm wondering. Was it Augustine, perhaps? Yeah.
You mentioned that. Yeah.
I'm wondering as well, though, if we actually have the correct physics in the model to represent the processes that we're interested in. Because I feel like at least in oceanography, we started at fairly coarse resolution. We made a whole bunch of assumptions, developed the numerical models, and then we got a whole bunch of computing power. And now we're using the same assumptions to model something at much higher resolution. I'm not sure if the assumptions hold. Is that same true in river sea systems, do you think? Or do we have a good grasp of the physics? I feel like I'm asking impossible questions.
Yeah. I can see Georg think. And I would like to know.
Well, I think we have quite a good grasp on physics, even in shallow water systems. I think the problem in these shallow water systems is much more on biogeochemical modeling and sediment transport modeling and so on. That's what I see is the real challenge.
Right. Yeah. Thanks, Georg. Okay, I think we've gotten to 33 responses. Now, the next question is, what should we focus on from a technical point of view when it comes to model development? Should it be, for example, the integration of model? I'm not going to say anything. I'm going to leave the floor open to the
audience. Crowd.
Exactly. Otherwise, I'm guiding the crowd. I'm dropping my points. Standards. From a standards point of view, I'm sure you guys are already engaging with the Open Geospatial Consortium, yeah? About the data formats and the API standards that they implement.
Now the answers are
coming. Formats, interoperability. Yeah. I imagine that interoperability is almost really important when it comes to integrating different modeling suites, yeah? Transferability. I mean, I'm intrigued by the word transferability. What do we mean by that?
Anyone of the audience who would like to comment could also use the chat or the questions box in
Absolutely.
the webinar.
Yeah.
Yeah. But number one is interoperability.
And
Now it's
parallelization.
parallelization. Yeah. Parallelization, because we want to run bigger models faster.
Covering larger areas. Yeah.
Larger areas.
Mm-hmm.
Yeah.
Integration of scales, parallelization, open source. Yeah. Okay. Reduction of data output. That's an interesting one.
I, for myself, would also have added flexibility.
Yeah.
What I see is that once we focused a lot on developing complete software packages with user interfaces and everything in it.
Yeah.
And nowadays a lot is done with Python scripts,
yeah.
for instance, gluing all kinds of components together for a specific study.
Yeah. 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 I wonder. There's also that. I mean, flexibility. You could also think of the ideas like a community model, for example, where all of the different model codes are kind of collated into a community model, where you then have options to use. You know, like the Delft flexible mesh or the Scheif. I don't know how to pronounce it, but I know that there were some activities to try and do that from an ocean modeling point of view, to try and get a little bit more of a community-based approach, so that we are better in terms of interoperability, intercomparisons. All of that makes life easier when you have a community model. But that is a huge development effort.
And another one might be openness of the systems. You can think of open source systems that are open for coupling to other systems, or computational cores that are freely available, and you can couple your own scripts and modules too.
Yeah. That's definitely interesting from an API point of view, where you can then, through the, like you were saying, with Python, you can connect to the different modeling platforms and do some fancy things to get the data that you need, or run the model in a way that you want to. Introduce new algorithms. Interesting. That makes me think of sort of the hybrid data like machine learning approaches that we're thinking about in terms of downscaling, for example, increasing resolution using machine learning approaches for boundary conditions.
We are working on this kind of modeling, hybrid modeling.
Exactly.
Where we combine numerical simulation with neural networks.
Yes.
And we also make use of remote sensing images. And this combination can be very powerful.
I saw a very interesting paper recently by the meteorological community, where they use a machine learning approach or a neural network to, instead of parameterizing subgrid scale processes, they use a machine learning approach to define that. It's quite an
combination is especially useful when you have particular fields of study that are very uncertain or chaotic or not well understood. And maybe a machine can find a solution.
Yeah, absolutely. I'm having a good laugh that documentation made it to the list here. That's brilliant. Okay.
Very well.
Here there was a comment from Marika about transferability. Maybe I mean the same as interoperability. We have a lot of parallel development. I think that it is inefficient to a certain degree. It would be good to transfer development and implementation of new processes into several modules. Yes, I think you mean about interoperability and transferability. That makes sense now. Thank you very much. Then the next comment is from Josias. The interoperability, the ability of data output or input to be used by different kinds of model with the same exception of results. I think it's like a standard. Yeah, we could debate that, but it is kind of like a standard, but for sure. Let's move on to the next, in the interest of time, let's move on to the next question. What are the scientific hot topics for future studies through models? These could range from sort of domain topics, for example, estuaries, rivers, or coasts, or oceans, or even from a numerical point of view, what are the hot topics, or data point of view. Climate change? Yeah, most definitely. I'm not going to say anything else. It's kind of morphodynamics. Yeah. Cumulative impacts and downscaling. Yeah. Water basin feedbacks. Yeah. So feedbacks is also an interesting one, and certainly if we're moving in this sort of Earth system science domain, then positive and negative feedbacks and actual coupling of Earth system type models. I think there's a lot of work to be done there.
Yeah.
Historic states of river sea systems. Yeah. Mars. Modeling river sea systems on Mars. Communication of model results. I'm surprised that pollution hasn't made the list yet. Because I think the river sea systems are very, very, very well placed to study sources to sinks, in a sense, from a pollution point of view.
Well, here is marine litter.
Marine litter, yes, fantastic.
Yeah, so the plastics. Plastics was put on the agenda because of the global garbage patches on the oceans.
Yeah.
But right now we are more and more aware that the river is a conveyor belt for plastic.
Absolutely, absolutely. And there's all this idea about doing ocean cleanups and that sort of thing. And really the problem is at the source, right? We have to start at the source.
Well, what's in the ocean is already there. We could prevent future pollution looking at the source.
Absolutely, absolutely. And I think we're also reaching a degree of resolution in the satellite remote sensing that you can already identify hotspots of pollution sources from space. For example,
I think that
sorry,
cumulative impacts. Sorry, I think that cumulative impacts deals also with pollutants.
Yeah.
That means the interaction of climate change, pollutants, sediment, transport, and so on.
Yeah, yeah. Yeah, I mean, if you look at the kind of nexus approach, like they often talk about a food energy. What is the last word?
Water, food, energy.
Water, food, energy nexus, where it's all of these cumulative impacts and interactions between processes and systems. Yeah. Great. This is a fantastic. Yeah. Donata?
I see uncertainty again. That for future studies, uncertainty is even more challenging.
Absolutely.
I think that we should rely on a multimodal approach, for example, as it's currently done in the IPCC studies.
Yeah, yeah, I would agree with that. And certainly, especially if you're talking about things like search and rescue and providing data to end users and stakeholders, I think the information about uncertainty of your prediction is really important, and an ensemble approach certainly would be beneficial to that. Okay, let's move on to the next one. So the last set of questions is about whether or not people want to be involved in Danubius activities. So the first question is, are you involved in Danubius? Or alternatively, you're not and you want to become. So that's great. If you are interested in becoming involved, we will share our contact details at the end. That I had a slide about that. Okay, lovely.
Well, it's now 50-50, so we can.
Yeah, I'm glad.
Our community.
Yeah, absolutely, absolutely. So for those of you who want,
it's even more important that the ones that are not involved, there's nobody that doesn't want to get involved. That's a very nice thing.
Yeah, absolutely. That is a testament to how important these activities are, these modeling activities are, and there's certainly a need to coordinate our activities, I feel, given the range of models that we're using, the range of challenges that we're facing. Great. Okay. Fantastic. So then the next question is, if you want to become involved, or if you're already involved in the DANUBIUS RI, which working group of the modeling node would like to participate in? The working group 1 is about spatially integrated models in RDS systems, river sea systems. Working group 2 is on interchange format, standardization of input-output. And I guess there was working group 3 was on post-processing, with, I think, a comment from one of the speakers that it could be expanded. The scope of working group 3 could be expanded. Water quality and pollution modeling was working group 4. Okay.
Well, that's evenly distributed. Well, most interested in spatially integrated models.
Yeah.
But nevertheless,
yeah,
I think the 4 groups, working groups, are well chosen.
Yeah, absolutely. Good.
Oh.
Fantastic. Yeah, great. Thank you very much. That's excellent. Would you like to have a quick discussion about how to expand working group 3? There was a comment by one of the speakers to expand the scope of working group 3 in terms of, at the moment it's focusing just on post-processing, but I guess the idea was to expand it to a little bit more. Not sure if anybody wants to contact. Was it you, Julia?
And I did not propose it. I think it was Jens, but maybe that's something that we can discuss within the working group. So anybody who's interested and has ideas how to expand it, please feel free to join and mention that, and then we can discuss it.
Lovely. Thank you, Julia. Jens, would you like to comment?
Could I ask back to explain me a little bit deeper what you are asking for?
Yeah, sorry, no worries. There was, I think you made a comment about expanding the scope of working group 3 because it was just post-processing at the moment, and you made a comment about expanding the scope of it. But perhaps it's, as Julia indicated, it's best discussed offline within the working group, considering also time.
Yeah. You're welcome. Well, it was just an idea in which working group to put questions of access steering of user interfaces to the DANUBIUS infrastructure. Where to put this topic?
Okay, right. Okay. I'll make a note of that, and then we can follow up on that later. Okay. Thanks, Jens. So finally, please feel free to suggest a new working group topic if the working group topics don't cover what you're interested in. For example, the graphical user interface topic.
Still silent, but you already asked so many questions.
We have asked many questions. I feel like maybe the audience is tired now.
Perhaps this means that we can intercept within the first 4 working group some sub activities more focused on specific issues.
Yeah, absolutely.
If I can add just one thing on the natural development of these working groups. So we, as DANUBIUS RI finished the preparatory phase last year, and everything is proceeding slowly. But now perhaps there is a chance to try to interact a little bit more within the working groups, no matter defining who is leading. I see as most fundamental the fact that we start to interact practically. So please use the contacts that you will find at the end for the first for the first contact for those that are not already involved. And then it will be Mai and Georg and Francesca Cure to try to start pushing the researcher of this community to work at the beginning by mail, and then perhaps with some dedicated meetings to go more in deep for the different topics. Any suggestion, practical suggestion on activities or priorities within the working groups are really more than welcome.
Great, thank you, Deborah. So let's take that as let's move on. And if you have additional comments for where to focus, please feel free to contact the Danubius Modeling Node group with the contact details that I'll show you at the end of this presentation. Moving on, how could the Danubius RI community best support you? Is it through tool provision and technical support?
Björn, sorry.
Yes.
Just back up because I saw some suggestions on other working group that perhaps can be collated. So the operational modeling seems to have a relevance and an interest, and so specific topics connected with the operational modeling is something we can think on. So let's just take note of this because it's
Absolutely.
important.
Absolutely.
Sorry, please go ahead.
No problems. The more interaction, the better. Okay. So how can Danubius help you? Tool provision and technical support, training with data, co-development of research. What is your preference? I love the fact that co-development of research is at the top of the list. So there's an appetite for collaboration, which is great. Certainly tool provision and technical support, yeah, those are some of the major challenges that we're facing. And data, yeah. Okay. Brilliant. Okay. Okay, so in the interest of time, I'm sorry, I'm going to move on to the next slide. And how else could the Danubius community support you if the previous 4 options weren't suitable for you? In just 2 minutes here, I think.
Yes, and then have a short wrap up.
Then we have a short wrap up, which Georg will facilitate for us. And then we can call it a day, I guess. There haven't been any comments on this particular slide so far.
Well, there's been plenty of opportunity to share ideas.
Absolutely.
Pointed topics that we should address.
Yeah. And as mentioned, increased networking opportunities. Yes. Sharing tools and models. And sharing.
Well, there is an appetite for networking and cooperation.
Yeah. Networking and cooperation. I'm not sure if the COVID pandemic has made that easier or worse for us. So I think in some ways it's easier because everything's been is online these days. In some ways it's worse because we don't get to see each other face to face.
Yeah.
A user forum, okay, yeah, that's interesting. Foster exchange on current topics.
But to start discussion in a community, these digital means are excellent.
Yeah. Okay. Okay, excellent. Thank you. Those are some great suggestions. And I have now reached the end of my presentation. So I will leave it now to Georg to wrap up and close the webinar for us. Thank you very much, everybody, for your attention. Over 3 hours now we've been here, 4 for some of us. And Georg, over to you.
Thank you very much. Just yesterday in Germany, they voted for the word of the year. And guess what? It was Corona. But anyway, if I have to vote for the word of the day for this webinar, it would be coupling. Yeah, coupling was everywhere. I mean, it was coupling hydrology and hydrodynamics. It was coupling of biogeochemical processes. It was coupling of sediments with morphodynamics, with, again, mercury, pollution, oxygen, and whatever. It was coupling between different models, between different scales of models. So I think this is one of the hot topics to be able to develop this kind of coupling processes and coupling models in order to make our systems and our models more usable. And well, the other point was format standardization and visualization, which was the other big point. And I think this is also very important. And as I already commented before, I think we should use DANUBIUS, the fact that DANUBIUS is an S3, is a European research infrastructure. It might become, hopefully, an ERIC in order to push these kind of things into communities where we would like to talk, and we would like to have a word in these communities. For example, this UGRID community, I think we should really try to lobby for this. And well, that's it. I think that was everything. And there is still, well, one point that was not so much discussed, but I really also would like to push for this, is the communication to the stakeholders, and the communication of uncertainty, which is extremely important. Especially, I'm involved in storm surge forecasting in Venice, for example. You can't believe how complicated it is to tell somebody that you have a forecast, but the forecast has a certain uncertainty. It's so complicated. And here we get into this social. We get the social touch also. We have to try to organize us in order to be able to communicate this. And I think that's all. I think the webinar was a real success. I loved it, participating. Hopefully also the other persons loved it. And the idea of having these Mentimeter questions was really something very nice. So my thanks to Deltares, to Björn, and to Joost, really for organizing this. Thank you very much. And for the others that were listening to us, please contact us, and we will then show you how to be able to contribute to Danubius and how Danubius could help you in your questions. Thank you very much.
Thank you, Georg. And Jens, waving. Would you like to say something, or no? Okay, never mind.
Just saying goodbye.
Okay. Goodbye.
So with that, I'd like to thank everybody for your participation, especially the speakers. Thank you very much for sharing slides up front in a timely manner, and also for presenting at our webinar. And we look forward to hosting or speaking to you again sometime soon. And I guess that we will communicate actions from our side with the community. And without further ado, I wish you all the best. Goodbye from us at Deltares.
Goodbye.
Bye.
Thank you.
Bye.
Thank you so much.
Bye.